In the vastness of space, there's a cosmic wonder that grabs our attention: the stars. These tiny lights, scattered across the night sky, invite us to explore the secrets beyond our home planet. Our journey begins on Earth, where the starry night unfolds like a giant picture. For ages, we've looked up, weaving stories and finding connections in the shining dots. Now, driven by curiosity and a thirst for knowledge, we're not just watching, we want to go further, to reach out and maybe even send our messengers to meet the mysterious distant suns that have fascinated us for so long. Today, I welcome you to join me on an expedition toward the closest stars to our home planet Earth. Around 4.6 billion years back, something big happened in a huge cloud of gas and dust called the solar nebula. It collapsed under the force of gravity, and from this collapse, a protostar formed at the center around it. There was a flat disk of material called a protoplanetary disk. As time marched on, this fascinating journey culminated in the birth of a dependable star, our very own sun, tirelessly burning hydrogen. This enigmatic transformation not only sparked the radiant existence of our sun, but also served as the dazzling overture to the captivating tale of our entire solar system, illuminating the origins of its radiant brilliance. The sun constitutes a vast 99.8% of our solar system, and the sun's immense size is highlighted by the fact that around 1.3 million Earths could fit inside it. This size contrast emphasizes the relatively small stature of our Earth compared to the sun. Orbiting the center of the Milky Way, the sun carries along the planets, asteroids, comets, and other solar system objects, traveling at an average velocity of 720,000 kilometers per hour. Despite this rapid speed, it takes approximately 230 million years for the sun to complete one full orbit around the Milky Way. At the sun's core, where nuclear reactions fuse hydrogen to form helium, temperatures reach a scorching 15 million degrees Celsius, with the core extending approximately 138,000 kilometers in width. Unlike Earth and other rocky planets and moons, the sun lacks a solid surface. What is commonly referred to as its surface is the photosphere. The term photosphere, meaning light sphere, is fitting as this layer emits the majority of visible light observable from the Earth. This star, the nearest to our Earth, is the primary catalyst for the video we are currently watching. However, within our Milky Way galaxy alone, there are around 100 billion stars. Let's delve into the exploration of the nearest one. Proxima Centauri, situated 4.2465 light-years away, is the second closest star to both Earth and our Sun. As part of the Alpha Centauri star system, alongside Alpha Centauri A and Alpha Centauri B, this triple star system resides in the southern constellation of Centaurus. Alpha Centauri A and B, resembling the Sun, constitute the binary system Alpha Centauri AB. Appearing as a single star to the naked eye, it stands as the brightest star in Centaurus and the third brightest in the night sky, surpassed only by Sirius and Canopus. Alpha Centauri A, also known as Rigil Centaurus, serves as the primary member of the binary system, displaying solar-like main sequence characteristics with a yellowish hue. It is approximately 10% more massive than the Sun, boasting a radius about 22% larger and ranking as the fourth brightest individual star in the night sky. The magnetic behavior observed on Alpha Centauri A mirrors that of the Sun, exhibiting fluctuations in its corona, which are caused by star spots influenced by its rotation. Known as Luhman, Alpha Centauri B serves as the companion star in the binary system. Alpha Centauri B, classified as a main sequence star, showcases an orange hue that distinguishes it from the primary star. Alpha Centauri B has approximately 90% of the Sun's mass and a diameter that is 14% smaller. In the X-ray spectrum, Alpha Centauri B emits more energy despite its lower luminosity. Proxima Centauri, alias Alpha Centauri c, is a faint red dwarf. Although not visible to the naked eye, it holds the title of the closest star to the Sun at a distance of 4.24 light-years, slightly closer than Alpha Centauri AB. Currently, the separation between Proxima Centauri and Alpha Centauri AB is around 13,000 astronomical units, equivalent to roughly 430 times the radius of Neptune's trajectory. Proxima Centauri is the host of two confirmed planets. The first is Proxima b, an Earth-sized planet in the habitable zone discovered in 2016, and Proxima d, a potential sub-Earth with a close orbit around the star, announced in 2022. If we consider the Alpha Centauri system as one, Barnard's star emerges as the third closest star to our Earth. It is a diminutive red dwarf star situated in the constellation of Ophiuchus, at a distance of 5.96 light-years from Earth. Its stellar mass is about 16% of the Sun's, and it has 19% of the Sun's diameter. Despite its proximity, the star has a dim apparent visual magnitude of 9.5 and is invisible to the unaided eye. It is much brighter in the infrared than in visible light. The star has a surface temperature of about 3,134 Kelvin. Most of its energy output is in the infrared band. Its solar luminosity in the visible part of the spectrum is only 0.004. To illustrate, if Barnard's star were placed at the center of the solar system, it would be 80 times dimmer than our Sun, and in that case life on Earth would not be possible. The red dwarf star has lost a lot of its rotational energy and takes 130.4 days to complete a rotation. In comparison, the Sun takes 25 days. The estimated age of Barnard's star is about 10 billion years, more than twice that of the Sun. The red dwarf may be one of the oldest stars in the Milky Way galaxy. Even though it is an old star, Barnard's star still experiences flare events and exhibits low-level magnetic activity. It shows coronal X-ray emission and moderately strong emissions in the ultraviolet band. Despite being twice as old as the Sun due to its low mass, Barnard's star will still be on the main sequence long after our star is gone. The life cycle of low-mass stars is much longer because these stars are fully convective and do not accumulate helium in their core. As a result, they can fuse their entire supply of hydrogen, not just that in the core, and stay on the main sequence for trillions of years. With a mass of 0.144 solar masses, Barnard's star may stay on the main sequence for over 2 trillion years, followed by a few billion years as a blue dwarf and finally a white dwarf. Blue dwarfs are a hypothetical class because the universe has not yet existed long enough for any star to have entered this phase. When Barnard's star evolves into a blue dwarf, it will have a surface temperature of 6,000 to 8,500 Kelvin and shine with a third of the Sun's luminosity. The star is old but will have some unique life than our Sun. Our third nearest star system consists of two brown dwarfs known as Luhman 16, situated in the southern constellation Vela at a distance of approximately 6.5 light-years from the Sun. These brown dwarfs are currently recognized as the closest ones in proximity. Luhman 16a, the larger of the two dwarfs, possesses a mass equivalent to 3.2% of the Sun, or 33 times that of Jupiter. Despite this substantial mass, its estimated radius is only 85% of Jupiter's, indicating a notably dense object. With a surface temperature of 1350 K, Luhman 16 falls into the spectral class L, suggesting the possibility of ongoing thermonuclear reactions inside it. Less is known about Luhman 16b, with an estimated mass of 28.6 times that of Jupiter. Its constantly changing brightness makes determining its radius challenging. It is classified in the medium class T, with a surface temperature reaching around 1200 Kelvin. Observations reveal that both brown dwarfs orbit each other in a slightly elongated orbit with a semi-major axis of 3.5 astronomical units and a period of 27.5 Earth years comparable to Saturn's period of rotation around the Sun. Spectroscopic studies indicate that brown dwarfs, rich in alkali metals like potassium and sodium, present challenges in estimating their age. The age of the Luhman 16 system is estimated to be approximately 510 million years, significantly younger than the Sun. Initial astrometric irregularities in the Luhman 16 system suggested the possibility of a third invisible body, possibly a planet. However, subsequent studies ruled out bodies larger than Jupiter, and there is still uncertainty about the existence of Earth-sized planets orbiting these brown dwarfs. Moving down the roster, we encounter another brown dwarf, an object of cosmic intrigue. This particular stellar entity goes by the name WISE 855-0714, with the latter numerical components denoting its celestial coordinates. Remarkably, this cosmic wonder is situated a mere 7.2 light-years away from Earth. WISE 0855 stands out as the coldest known object outside our solar system. It's only detectable in infrared light, requiring powerful ground-based telescopes. Essentially, it's a celestial underachiever, similar to stars in formation, but lacking the mass for nuclear fusion that lights up stars. The brown dwarf, with a mass approximately 5 times that of Jupiter, shares an uncanny resemblance to the gas giant planet. In terms of temperature, this cosmic entity registers at about 250 Kelvin, placing it in close thermal proximity to Jupiter. As we conclude this segment on our closest stars, the intriguing possibility of habitable planets around brown dwarfs remains a topic of interest. Future chapters in this series will explore more celestial wonders. If you enjoyed this video, please subscribe for more content, and we look forward to continuing our journey in the next episodes.